At 8:48 in the morning on July 17, 2026, the seafloor off the southern coast of Mexico gave way. 48 kilometers southwest of a small coastal town called Aquiles Cerdán, two tectonic plates that had been locked together for years finally slipped. Magnitude 7.3. The shaking lasted well under a minute. Here is what you will know by the time this program ends. You will know why two of the world's most trusted seismic agencies published depths for that same earthquake that differ by 10 kilometers, and why that 10-kilometer gap is the single most important number in this entire story. You will know the exact statistical rule that predicted, almost to the decimal, how large this earthquake's biggest aftershock would be, and the one specific threshold that would tell scientists this sequence has stopped behaving normally. Hold on to that 10 kilometers. You are going to need it. That first minute of shaking is already over. It ended before most people in Chiapas had time to get out from under a doorway. What is not over is everything that came after it. A string of aftershocks that kept arriving for days, and a stretch of ocean floor that, by the numbers, produced more earthquake activity last week than almost anywhere else on the planet combined. That is what scientists are still watching. That is what this program is about. Start with what is settled. The United States Geological Survey placed the origin time at 14:48 and 39 seconds Coordinated Universal Time, 8:48 in the morning local time, with a depth of 15.2 kilometers. Mexico's National Seismological Service, working from its own network of stations, placed the epicenter about 135 kilometers southwest of the town of Ciudad Hidalgo. Roughly 88 minutes earlier, a smaller magnitude 4.7 tremor had struck nearby. A quiet warning nobody could have read as one at the time. Shaking reached Mexico City, more than 600 kilometers away, and was felt in Guatemala City and San Salvador. The Watchers, a seismic monitoring service that aggregates felt report data, estimated that roughly 67,000 people experienced very strong shaking, another 627,000 felt it strongly, and more than 3 million felt it at moderate intensity. The USGS's Rapid Damage Assessment System, pager, put about 208,000 people inside the zone of strongest ground motion. Those numbers are not in dispute. Remember them, because what comes next is where the agreement stops. Picture the coastline itself for a moment, because this did not happen under a skyline. It happened under fishing villages and small ports, coffee and banana country climbing into the hills behind them, and one mid-sized city, Tapachula, home to roughly 200,000 people, close enough to the border that Guatemalan radio comes in as clearly as Mexican stations do. Puerto Madero, the working port nearest the epicenter, is where the tsunami gauges recorded a wave of 33 centimeters. This is a landscape built for withstanding earthquakes rather than avoiding them, because for the people who live there, avoiding them was never an option. This stretch of coast has absorbed a major earthquake roughly once a generation for as long as records go back, and its building codes, its evacuation drills, its civil protection offices carry that inheritance in every design decision. You should know this fact before anything else. An earthquake as large as magnitude 7.3 happens only about 15 times a year anywhere on the planet. That this one produced cracked walls and gas leaks instead of collapsed buildings is not luck. It is what decades of preparation for exactly this scenario looks like when it works. And it did work. A handful of people were injured, none critically, and no deaths were reported. Civil protection crews in Chiapas responded to cracked walls, a few collapsed sections of roof, isolated gas leaks. Villahermosa in neighboring Tabasco evacuated several buildings as a precaution. Guatemala closed schools in 4 western departments after minor landslides. Oaxaca's governor called the shaking there moderate, with no significant damage. Mexico City's automated earthquake alert system, built after the 1985 earthquake that killed thousands in the capital, never even activated, because the shaking there, though felt, stayed under the threshold that triggers it. The tsunami warning was lifted a little over 2 hours after the quake. If the story stopped here, you would already have the whole thing: a major earthquake, a coastline that was ready for it, and ending with no casualties. It did not stop here. Before going further, you need one piece of arithmetic, because it explains everything that follows and most people get it wrong. Earthquake magnitude is logarithmic. Each full step up releases roughly 32 times more energy than the step below it. Not 32% more, 32 times. Do that math on this sequence, and the numbers get uncomfortable fast. The magnitude 7.3 main shock released something on the order of 90 times more energy than its own largest aftershock, a magnitude 6.0. It released roughly 20 times less energy than the magnitude 8.2 earthquake that struck this same coastline in 2017. And set against the most powerful earthquake modern instruments have ever recorded, magnitude 9.5, Chile, 1960, July 17th was smaller by a factor of several thousand. Keep that scale in your head. It is the reason a step or two in either direction on this same number line is the difference between cracked plaster and 100 deaths. Now, you are ready for the actual mystery, and it starts underground, literally. The Gulf of Tehuantepec sits above one of the most active plate boundaries on Earth. Offshore, the Cocos Plate is diving beneath the North American Plate at a measured 6.4 centimeters a year. Slow to a human eye, relentless over a human lifetime, all of it resisted by friction until the rock finally breaks. This particular stretch of coast breaks constantly. Within 300 kilometers of Chiapas, an earthquake of magnitude 4 or larger strikes on average once every 8 hours. Earthquakes above magnitude 7 have hit the same general area at least 6 times since 1900, roughly once every 20 to 25 years. This was not a quiet corner of the world waking up. It is one of the planet's more productive earthquake factories, and July 17th was simply its latest shift. Here is the question you actually came for. Exactly where, inside that machine, did this earthquake happen? A subduction zone is not one fault. It is at least 2 separate earthquake-generating systems stacked on top of each other in the same patch of ocean. The first lives on the interface, the surface where the descending Cocos Plate is still pressed directly against North America. Earthquakes there are the ones capable of growing into magnitude 8 and 9 events because the locked patch they can rupture is enormous, and because a large vertical shift on that surface is what generates a dangerous tsunami. The second system lives deeper, inside the Cocos Plate itself, below the point where it separates from North America, the plate bending and stretching under its own weight, breaking along an entirely different set of faults. Geologists call those intraslab earthquakes. They can be powerful, but mechanically they are a different animal, and they do not carry the same tsunami risk. Depth is the number that tells you which of those two systems fired. A shallow rupture, 10 to 20 kilometers here, points toward the interface. A deeper one, 30 kilometers or more, points toward the slab bending beneath it. And this is exactly where the two agencies tracking July 17th stopped agreeing. Remember that number from the opening? Here it is. The USGS placed the main shock at 15.2 kilometers. The European Mediterranean Seismological Center placed the same earthquake closer to 25 kilometers, 10 kilometers apart. Not a rounding error, the gap between a shallow interface rupture and something happening well inside the descending plate, which is the difference between the fault most capable of a truly catastrophic earthquake and one that, mechanically, is not. Why would two respected institutions disagree this much about something this basic? The reason is almost dull, and once you hear it, you will never read a depth figure the same way again. Earthquake depth is calculated largely by comparing the arrival times of seismic waves that travel straight to a station against waves that bounce off the surface first. That works well when instruments surround the earthquake on every side. An earthquake 50 kilometers out in the Pacific offers no such luxury. Every station recording it sits on shore, in one direction, so the geometry available to solve for depth is lopsided from the start. Different agencies also run different velocity models, different assumptions about how fast seismic waves move through that specific slice of rock, and feeding the same waveforms into two different models can honestly produce two different answers. Neither agency made an error. Both published their best solution to a measurement that is by its nature difficult offshore. And both published the disagreement openly rather than hiding it. That same uncertainty runs straight through the aftershock sequence, and once you know to look for it, you will spot it immediately. Catalog after catalog lists these aftershocks at a depth of 10 kilometers, then 10 kilometers again, then 10 again, and then, without warning, one jumps to nearly 45 kilometers, another to 35. You are not looking at real geology when you see that pattern. You are looking at software. When an automated system cannot pin down a depth with confidence, many catalogs quietly substitute a fixed default, commonly 10 kilometers, rather than publish no answer at all. Some of those repeated 10s are genuine measurements. Others are simply the system's way of shrugging. Sorting out which is which takes a human seismologist reviewing the raw waveforms by hand, and for a sequence this size, that review takes days. While that depth question sat unresolved, the sequence itself was doing something worth tracking on its own terms. In the hours after the main shock, at least 10 aftershocks between magnitude 4.9 and 6.0 struck the same stretch of ocean, according to data the Associated Press attributed to the USGS. Here is the number I promised you at the start. Seismologists have a rule of thumb called Bath's Law. The largest aftershock following a main shock typically lands a little over 1 full magnitude step below it. For a 7.3, that arithmetic predicts a largest aftershock somewhere close to magnitude 6.1 or 6.2. The actual figure, magnitude 6.0, landed almost exactly where a century of earthquake statistics said it should. You can treat that as the sequence handing in its homework and getting the answer right. And here, finally, is the threshold I told you to wait for. This is the specific number that would tell scientists something had actually changed. Bath's law says a main shock this size should not produce a second aftershock anywhere near magnitude 6. 1 is expected, 2 would not be. If a second magnitude 6 or larger event had appeared in this sequence, that is the signal that would move this from an ordinary aftershock story to something requiring real concern. As of the most recent catalog data examined for this program, that has not happened. The ceiling on this sequence remains 6.0. Behind the scenes, this is also where the USGS's aftershock forecasting system goes to work. For an earthquake this size, the agency runs a statistical model built on decades of catalog data from sequences just like this one, plus the same Bath's Law arithmetic you just heard, and publishes a running set of probabilities. The chance of at least one more magnitude 5 in the coming week, the chance of a magnitude 6, updated automatically as new data arrives. It is not a prediction in the sense most people mean the word, and it cannot tell you whether a larger earthquake is coming. What it can tell you, continuously and transparently, is whether the numbers coming out of Chiapas are tracking with how sequences like this one have behaved elsewhere, or beginning to drift away from that pattern. Through the days examined here, they were tracking with it. By the days that followed, the aftershock rate had begun to slow, the way sequences like this are expected to slow, under a pattern seismologists call Omori's Law, a burst right after the main shock, then a decay that is fast at first and stretches out gradually over days and weeks, never dropping to zero all at once. Catalog data through the following Monday still showed aftershocks arriving off the Chiapas coast, but at smaller magnitudes, mostly in the low 4s, a clear step down from the 5s and 6s of the first day. That is what a sequence returning toward background levels looks like from the outside, even while individual jolts remain large enough to be felt onshore. That covers what happened in the days right after the rupture. It does not yet explain why an earthquake this size, in a place this well studied, still leaves scientists watching a screen rather than closing the file. And that answer is sitting in this coastline's own history. If you want the next update the moment the reviewed depth data settles that question, subscribing is the easiest way to have it land in front of you without going looking for it. 9 years earlier, almost to the week, the same general region produced the most powerful earthquake to strike Mexico in generations. On September 7, 2017, a magnitude 8.2 earthquake ruptured beneath the Gulf of Tehuantepec at a depth of 47.4 kilometers, deep enough, with a fault mechanism distinctive enough that seismologists classified it as an intraslab event, the plate tearing under its own weight rather than a shallow thrust along the interface. It killed 98 people, injured hundreds more, caused an estimated $4 billion in damage, and was followed by more than 3,800 recorded aftershocks. Sit with what that earthquake proves on both sides of the ledger at once. This stretch of subduction zone is fully capable of producing something nearly 100 times more powerful than what just happened, and when it does, the mechanism underneath it can look completely different from the one behind this earthquake. A decade before that, in October 1995, A magnitude 7.2 struck the same general area at a depth of 159 kilometers, so deep it barely resembled a coastal hazard at all. A reminder that the descending Cocos plate keeps generating earthquakes long after it vanishes from view. Widen the lens further, and this stops looking unusual at all. The Gulf of Tehuantepec sits on the same general belt of subduction zones that produced the largest earthquake ever instrumentally recorded, magnitude 9.5, Chile, May 1960, and the magnitude 9.1 earthquake that triggered the Indian Ocean tsunami off Sumatra in December 2004. Every one of those shares the same basic architecture as the ground beneath Chiapas, an oceanic plate sliding beneath a continental one, friction locking the two together until accumulated strain exceeds what the rock can hold. What differs from one subduction zone to the next is not the mechanism. It is the bookkeeping. How much strain has built up, how recently it was last released, how deep the locked patch runs. Mexico's Pacific coast has been measured and mapped for exactly that bookkeeping for decades, which is part of why an earthquake here arrives surrounded by context rather than as a total surprise. None of that history answers the one question you are probably asking right now. Could this be a foreshock? An early tremor ahead of something considerably larger? You deserve the honest answer. Not a comfortable one. Nobody, not the USGS, not Mexico's seismological service, not any research group anywhere, has a method that can identify a foreshock while it is happening. The label only ever gets applied afterward, once something bigger follows. Statistically, the overwhelming majority of moderate earthquakes are never followed by anything larger. Global figures put those odds within a matter of days at roughly 6% or lower, but 6% is not zero, and the clearest reason the caution matters comes from Japan. 2 days before the catastrophic magnitude 9.0 Tohoku earthquake in March 2011, a magnitude 7.3 struck the same stretch of coastline. At the time, seismologists treated it exactly as the statistics said they should, a significant earthquake in its own right, with its own ordinary aftershock sequence. Only in hindsight did it become the most consequential foreshock in modern seismic history. That is not a prediction about Mexico. It is the honest limit of what the science can currently do, and pretending otherwise would serve you worse than the uncertainty itself. One more thread, and it reaches beyond Chiapas entirely. In the days after the main shock, moderate earthquakes were logged elsewhere along the wider Caribbean plate boundary, off the Pacific coast of Nicaragua, roughly 700 kilometers away, and near Grand Cayman, more than 2,000 kilometers from the Mexican coast. It is natural to wonder whether one earthquake set off the others. Seismologists study this under two different mechanisms. Static stress transfer is well documented. A rupture measurably changes the stress on nearby faults, nudging some closer to failure, but it is short-ranged, meaningful only within 1 or 2 rupture lengths, which for a 7.3 means a few hundred kilometers at most. Grand Cayman sits roughly 10 times that distance away. The physics does not reach that far. Dynamic triggering works differently. The seismic waves themselves can occasionally nudge a fault already sitting at the edge of failure, documented at distances of 1,000 kilometers or more, most famously after a major 1992 California earthquake set off small tremors across the western United States. It is real, but weak, and it only moves faults that were nearly ready to slip on their own. Put plainly, the Nicaragua earthquakes on the same subduction system at a more plausible range deserve a second look. Grand Cayman, on an entirely different boundary that produces earthquakes on its own schedule every week, is most likely coincidence dressed up by timing, so gather everything you now know and look at the honest gap left in the middle of it. A historically active subduction zone released a magnitude 7.3 earthquake. Its aftershock sequence arrived in numbers and at a peak magnitude that match a century of statistics almost exactly, and the one threshold that would have signaled real trouble, a second magnitude 6, has not been crossed. The depth of the main shock and of the aftershocks that followed it remains genuinely unresolved between the agencies best equipped to measure it, which means the deeper question, interface or slab, the fault capable of the largest earthquakes, or the one that mechanically is not, does not yet have a confirmed answer. Reviewed, human-checked depth solutions were still being finalized as this program was produced. When they publish, they will do more to settle that question than anything said here. Here is what you can say with confidence right now. What changed is observable and finite. A section of the Cocos Plate boundary that had been storing strain for years released a measured amount of it in under a minute, and the crust around that rupture spent the following days redistributing the leftover stress through a declining series of smaller earthquakes, exactly the way a subduction zone under this kind of load is expected to behave. What did not change is the machine underneath it. The Cocos Plate is still descending at 6.4 centimeters a year. The interface is still capable, as 2017 proved without ambiguity, of producing an earthquake many times larger than this one. And this region will keep producing an earthquake above magnitude 4 roughly every 8 hours, as it has for as long as instruments have been listening, because that is simply the pace at which this boundary between two tectonic plates does its work. None of this ends when the last aftershock drops out of the catalog. Mexico's National Seismological Service and the country's civil protection agencies maintain permanent networks of seismometers and GPS stations along this coastline for exactly this reason. A single earthquake, however well recorded, is only one data point in a much longer study. Every rupture adds to a record stretching back decades, and that record feeds directly into the hazard maps behind the country's building codes. The same codes that, judging by how little damage a magnitude 7.3 produced this time, are doing the job they were written for. Once the reviewed depth solutions for this sequence are finalized, they too will be folded into that record, sharpening every future estimate of exactly how this stretch of coast tends to fail. That work is unglamorous and largely invisible unless you know to look for it. It is also why saying scientists are still watching means something more specific than it might sound. They are not waiting nervously for a verdict. They are doing the same patient measurement they do after every earthquake on this coast, because that patient measurement is what eventually turns raw shaking into genuine understanding. That is the honest shape of the answer you were promised at the start. Nothing about July 17th represents a change in what this stretch of the Mexican coast is capable of. What changed was that the ordinary, relentless grinding of two plates against each other became visible for a few days, close enough to instruments that scientists could watch it happen in near real time, the aftershocks arriving, the depth estimates disagreeing, the statistics holding up against the data as it came in. Coastal Mexico did not discover a new hazard in July of 2026. It was reminded with unusual clarity of an old one that has been quietly shaping that coastline for millions of years, one rupture at a time, long before anyone was there to measure it, and long after the last aftershock from this sequence finally goes quiet. This is the kind of story worth following as the evidence comes in, not just once when it breaks. If that steadier, fact-first way of tracking the planet's biggest stories is what brought you here, subscribing means you will see the next update the moment it publishes.